Okay, hello everyone. Let's see this question. It says find the value of the resistor RL in the figure below given maximum power dissipation and determine the value of this power. Okay, I would like to let you know that at maximum power that the Thevenin's resistance it must be equal to the load resistance. So when you find the Thevenin's resistance, it is equal to the load resistance. Okay, so that now leads us to the maximum power. Now the maximum power in a circuit in that case now will be equal to the Thevenin's resistance, the square of the Thevenin's resistance all over 4 times square of the Thevenin's voltage divided by 4 times the Thevenin's resistance, or you can just say the load resistance. And with that, we are done. Okay, so your knowledge on Thevenin's theorem is important here. So the first step in Thevenin's theorem solution is to remove the load resistance and make it an open circuit. So making it an open circuit, we can calculate the voltage across the 12 ohm resistor. Okay, that's the 12 ohm resistor. Now, but we can also see that since this is an open circuit here, the 3 ohms and the 12 ohms resistor are in series. So I can simply use voltage dividers rule, okay, to solve that, to find the voltage across the 12 ohm resistor. Because obviously my VTH now, the only voltage in this VTH cycle is the voltage across the 12 ohm resistor. So if we continue, you can see there that the VTH, according to voltage dividers rule, is 12 all over 12 plus 3 times the total voltage, which is 15. Okay, and that is giving us 12 volts. So my VTH is 12 volts. Okay, then now we can now go ahead to find RTH. How do we find RTH? Remember, in RTH, you close, to find RTH, replace all voltage source with a closed circuit, then all current source with an open circuit. In this circuit, we don't have a current source, so this is what we do. When we replace all the voltage source with a closed circuit, we have this. You see that? And now from that diagram, it is obvious that 3 ohms resistor is in parallel now with the 12 ohm resistor. They are no longer in series since all the voltage sources are closed. So we can find the RTH. The RTH will simply be 12 times 3 all over 12 plus 3 as the parallel connection between 3 and 12 ohms. And you see there we have 2.4 ohms. So we've answered the first question, which is to find the value of RL. We say that at maximum power, that RL is equal to RTH. So we can conclude here that RL is also equal to 2.4. Okay, so then the maximum power from the formula I gave you is VTH squared all over 4 times RTH. And when you substitute the value, you see that my maximum power is 12 watts. Okay, so we'll move to the next question. Now here we are asked a transformer was locally made with N1, that's the primary core, 120, N2, that's 100. Okay, now mu1, that's relative permittivity, is 2000, and relative permeability, sorry, is 2000, and the length of the coil is 80 centimeter. Now, if this transformer was wired with a cross-sectional area of 100 times 10 to power, 100 centimeter square, what will be the mutual inductance in the secondary coil? Now, we're going to be using the formula that our mutual inductance is the relative permeability multiplied by the permeability, then N1, N2A all over L, which is the length. So if we substitute that value, we are going to have this. The relative permeability is 2000, then permeability of free space is 4 pi times 10 to the power minus 7. Okay, I would like to say here that the relative permeability shows that the transformer is in a medium that is not vacuum. Okay, so but if the medium was vacuum, then we will not need to bother with that. So your N1 is 120, your N2, okay, I think I reversed. Okay, N1 is 120, N2 is 100. Then the area is 100 centimeters square, which if we convert will be 100 times 10 to the power minus 4 meters square. Then divided by length. The length is 80 centimeters, which is 0.8 conversion. So our answer gave us 0.375 Henry. Okay, that's beautiful. Now we see another question here. It says a step-up transformer is designed to have an output voltage of 22,000 volts. Okay, when the primary output voltage also means the secondary voltage. When the primary is connected to a 100 VRMS source. Okay, so if there are 80 turns in the primary windings, calculate the number of turns in the secondary windings. This is a straightforward question. So here you can see the turn ratio, no, not turn ratio, sorry, EP over ES is equal to NP over NS. But I want to make something a little clearer. If you're asked to find turn ratio, please always note that turn ratio means the number of turns in the secondary coil divided by the number of turns in the primary coil. That's if you're asked to find the turn ratio, we call it turn ratio. Okay. Okay, so please note that. But in this case, this is not the case. So we have EP over ES, that's the EMF of the primary coil over the EMF of the secondary coil is equal to the number of turns in the primary coil is all over the number of turns in the secondary coil. Okay, so we have this. When you substitute the EMF for the primary coil is 100 from the question, then 2,200 for the EMF for the secondary coil. The primary coil have 80 turns, so we are looking for the number of turns in the secondary coil, which when you cross multiply, you get 1,600. Okay, that is quite easy. Then our last question here. A 60:1 output transformer is used to match output transistor to a 4 ohms voice coil. Okay, now find the impedance of the output circuit. Now there's a relationship between number of moles and number of turns and impedance, and this is it. The number of turns in the primary coil, the square of the ratio of the number of turns to primary coil to that of secondary coil is equal to the impedance of primary to that of secondary. Okay, and we have this. So 600 or 60 over 1, because 60 ratio 1 all squared is equal to 4 over ZS. We are looking for the impedance of the output circuit, which is the secondary coil. And with that, we'll get making ZS some little formula. We'll get this formula. Okay, thank you very much. I wish you the best in your exams.